Let's look at voltaic cells in non-standard conditions. What happens is a galvanic or a voltaic cell is discharged. So at the start, the concentrations of the ions in the solution are originally each a 1 molarity solution. The reactant concentration will decrease over time and the product concentration will increase. The potential voltage will decrease, and this will keep going until it reaches equilibrium. At equilibrium, we call that a dead battery, so there's no more power flow. At equilibrium, the value of E would be 0, and the value of our free energy, G, would also be 0. Remember, G is 0 whenever you're at equilibrium. So the galvanic cell is never at equilibrium until it is a dead battery, till it runs its course. Then it is considered at equilibrium. E naught corresponds to standard conditions of Q equals 1. And also we would have a 1 molarity concentration. We would be at room temperature, 25 degrees Celsius. As the cell runs down, though, it approaches that equilibrium when Q equals K. So we can calculate Q and compare it to 1 to figure out what our voltage is going to be. So if Q is less than 1, then the voltage will be higher than normal. If Q is bigger than 1, the voltage is lower than normal, and that is because it's closer to equilibrium. If it's bigger than 1, it also has more products than reactants. So you would use the Nernst equation, and the whole idea, if you find just the Q, it just saves you time, because this equation is quite lengthy to figure out. It is given to you on the data sheet, but it takes a while to put all the numbers in. So if you can focus on just the Q and remember we do products over reactants, we can find that Q, see how it compares to 1 to figure out if the voltage will be higher or lower than normal. If they want a specific voltage at non-standard conditions, then you would have to go through and solve for the Nernst equation. So let's do this problem. As the cell is running down, the original conditions, we have our energy potential, our voltage potential would be at 2 volts. Let's change the concentration to these new concentrations. So, and answer this question, will this change the voltage? Will there be more? Will there be less? So let's just analyze what's going on here. So we have our copper ion is 0.5 and our aluminum ion is a 2 molar concentration. We can solve for Q, and remember it's products over reactants and don't include any solids. The other components, they are solids, I just didn't write them. So I'm only going to do those, the aqueous ions, and on the test you would have this information. So let's go ahead and put our numbers in here so we can see what our Q is. So we have a 2 and it's squared divided by our copper and it's cubed, and when I do the math I get a 3.2. So I know that this is bigger than 1, so my Q is bigger than 1, and so because of that I am going to have a lower voltage. I'm going to have more products than reactants, and figuring out this little Q just helps me figure this out faster. You could go through and figure out the Nernst equation, and I'm just going to press the button to show you that I have figured it out. So plugging in all the numbers, and then you can tell right here that's my Q that I did before, and here's those numbers that I plugged in before, and I get my voltage as 1.99 volts, and so this would be a decrease, and it's a very, very small decrease, but it is a decrease nonetheless. So again, if that Q is bigger than 1, then we're going to have lower voltage. Let's revisit this same problem. So again, our normal cell potential would be a 2 volt. This time, let's change it so that we have 2 molar concentration for the copper and a 0.5 for the aluminum. And so will this change the voltage? Will it be more or less? So I'm going to solve that Q. So I'm going to put my products on top and my reactants on the bottom. And let's go ahead and plug our numbers in. And my number is 0.0313. So I see that my Q is much less than 1. And so this means that I have more reactants than more products. It's a little bit more than normal. And so I'm going to be able to have an increase in voltage. So I'm going to have more voltage. You can plug all your numbers into the Nernst equation, and I've already done that, and I'm going ahead and press the button. So there's my Q that I just solved, and I have my products over my reactants. Plugging all the numbers in, I get just a slight increase in that voltage, just with the change in the concentrations of the solutions. Let's look at a different problem, and this one is different. My ratios are 1 to 1 for the ion in the reactant side and the ion in the product side. Let's see, instead of having a 1 molar concentration, what if I double everything? So will this double the voltage? So let's look at our Q, and again, products over reactants. And look, I wrote the solid and the aqueous, except for this last one. So yay me. Let's go ahead and put the numbers in. So they're both 2 over 2. So when I figure this out, I get Q equals 1. And so this tells me that even though I've doubled the concentration, I will have the same voltage. So just doubling the concentration of your liquids in your cell doesn't mean that you're going to get double the voltage. If you had a ratio that wasn't 1 to 1, it might be a little bit different, but in this 1 to 1 ratio of our equations, again, our Q would be 1 if you double everything. And so you don't change the voltage at all. And so here's figuring this out, and you can see that the voltage is the same. Let's look at a concentration cell. So in this concentration cell, it's a little bit different than you might have seen before. It is the same electrodes, so the same metal. The only difference is that we have a dilute solution and then we have a concentrated solution. And for this, the electrons are going to flow from the dilute to the concentrated solution. And this is considered non-standard conditions. If we go and we plug in the concentrations of our dilute cell and also our concentrated cell, so we're going to have the concentration of the dilute cell divided by the concentrated cell. We do see that we have a little bit of power that is generated from a situation such as this. So not a lot, but a little bit. And this will keep running until everything's at equilibrium, until the concentrations are the same on either anode or cathode.